All right, so announcements before we get started. Obviously, we have the 8th tomorrow. We have. What else? We have a new assignment in this course, but it's not going to be due for a week and a half. That said, it's the biggest assignment by far so far in this class. And I want to just put that out there as this is not something you can get done in a day or two. This is going to be something, there are 4 large parts to it that are probably close to the size of a previous homework. So that means that you will want to get started early. Obviously, I would not get started before the 8th for those of you who are taking 8, focus on the 8th. But this weekend, get stuck on this homework and come back on Monday with questions and then work on it throughout next week. There will be an exam a week from tomorrow in the class, but kind of half and half focus maybe between the assignment and the exam throughout next week. We will again have a study session next Thursday where you can come with any questions and I can go over any practice for that. But it's starting to get real in here. There's a lot going on right now between the 8th, the exam next Friday, and this assignment. As always, I'm here to support you as long as you're putting in the work. I think that's everything from this class's perspective. Does anyone have any questions before we get started on new material?
Oh, I apologize. What was our agenda for tomorrow? I think you said it, but I was.
Yeah, so for tomorrow, my plan at the moment is new content because it's not right before the 8th. In 212, though, I plan to have an 8 study session. So people from this course, if you're free from 12 to 1, are happy to pop by and ask questions. Let's treat it like an open forum. Let's just go over any last minute questions you have for the 8th. I'm kind of open to doing that in this class too, if people feel like that would be useful for your studying. So let me know. We're in a pretty good place with regards to the content that we've covered. And I had set aside all of the last week of this course to be practice problems. So to be on pace for that means that we have a week at the end of the course to just practice everything that we've learned.
Out of curiosity, how does that, and maybe you don't have it decided, but how many homework assignments do you think you'll?
I create those kind of on the fly as needed and kind of figure out the due dates for those as well. So I want to make an assignment for cache tables. I want to make an assignment for advanced sorting, for trees and searching trees, for graphs. So probably about 4 more. We'll see if that comes to fruition or not. I plan on using that last week as well for homework or to have a homework and to catch up where we don't have new content just because the pace of this new content has been pretty fast. Other questions, other concerns? Do people prefer an 8 study day tomorrow? I can do something like that. We can at least, we can do that until we run out of questions or things to go over. Transition, we can always transition to new content on an as needed basis. Sets and hash tables. So the motivation for discussing sets is that they are. We've all seen sets before, right? Hopefully somewhere discrete. If not in discrete, then in some math class, we know what a set is. Ish. So we want some kind of structure that's going to mimic a mathematical set. So a set has a couple of important restrictions. Who can name those restrictions? So yeah, unique, which means there's no multiplicity. What's the other one? Other big one?
Not really in any like particular order.
Yeah, order does not matter. Exactly right. So order is irrelevant and multiplicity is irrelevant. So the set that contains 1, 2 is equivalent to the set that contains 2, 2, 1, 2, 2, 1, 1, 1, 2, 1, 2. Same set. They both contain 1 and 2. Multiplicity doesn't matter, order doesn't matter. From a computer science perspective, we don't want to store all of those multiple values. So we want to make sure that there is only at most one of a particular element in a set. So order doesn't matter, multiplicity doesn't matter. Starting to think about the tools that we have seen so far, does it make sense for a set to be modeled based off of an underlying list?
No.
Yeah, a list has an underlying order to it. We have an index that we could query. So if we were to do a dot equals on a list and that reversed list, would we get true or would we get false? We get false, it's not the same object. Whereas with a set, we would want to return true because order does not matter in a set. So we already have reasons that we can't just plug and play a list. There's another big concern with using a list. What do we think that is?
Or sorted. Other things that was consorted.
We can do things like sort a list, yeah?
Like it stores.
Oh, got it. Yeah, the list can store duplicates, absolutely. So we have no guarantee. What would it look like to make sure that we don't have duplicates in a list? What would that algorithm look like?
We probably need like another list that stores unique elements and search through your main list.
Yeah, you basically have to search through the list for duplicates. And the best you can do with that is a linear search. You can't do something like a binary search because again, order and multiplicity don't matter. So you can't assume that it's sorted or the underlying structure is sorted. So you can't do a binary search for an element. So you need to do a linear search for that, for any elements. If you don't have that algorithm from the beginning, or you want to convert something into a set, then just because you find a duplicate element doesn't mean that that's the only duplicate element. There might be 50 of those elements. So just because you find something doesn't necessarily mean that you're done. So the main other concern is efficiency, in that every add and remove from a set is going to be linear because we need to figure out, is it already there? And or how many copies of this already exist and try to remove them. So efficiency is linear for operations that we would like to be faster than linear. There's nothing wrong with it being linear, except that there exist better solutions. And whenever there exist better solutions, we want to implement better solutions. So let's first talk about what we would need to be able to implement in a set. So the set is another abstract data type that we've covered. So we've covered lists, we've covered stacks, we've covered queues, and each of those have multiple possible underlying representations that represent what we're trying to model. So a stack can use an array list, a stack can use a linked list, a list can be an array list, a list can be a linked list. But we haven't seen underlying structures that aren't lists yet. Everything that we've studied so far has had a list as an underlying structure. So let's think about the functionality that we want from a set, and we can think of, is there a better way to do this? So first, we want to be able to add an element to the set. So adds an element to the set and returns true. If the set already contains it, then we return false. So were we successful at putting this into the set? If we were, we return true. If we are not, we return false. That just gives us a little bit of information that we could possibly use, like did it already contain it? We want to be able to add an entire collection at once. So we're just like we had with a linked list add all, there's an add all for a set. Now note that this set could be, this collection that is passed in could be any kind of collection. We could say something like pass in a linked list and add every element of this linked list. We could say pass in an array list and add in every element from this array list. So it just takes a generic collection, and there are other collection types that we have not discussed so far. So it adds all elements from the collection to the set, of course, ignoring order and multiplicity. So as we're parsing the collection, we need to figure out, is it already contained in the set? If so, don't add a duplicate copy of it. Because the collection that we pass in isn't necessarily a set and may have duplicates. We want to be able to clear the set, remove all elements that already exist in the set. We need to query whether or not a particular element is in the set. We call that contains. So true if it contains the parameter object, false if it does not. Contains all takes a collection and returns true or false, whether every element of the collection is in the set, yes or no. We of course want to implement an equals. Now, whenever you implement, I don't know how well 211 covered this, but whenever you implement an equals, you don't want to pass in something that's of the same type because you want to be able to determine the equality of things like a set and a giraffe object. They're obviously not equal, but if you assume that equals takes a parameter that is a set, then you're not going to be able to return false for comparing it to another object type. You can only then compare sets to sets. So we want to be able to compare sets to any other object, which means that the equals method does things like check the class of the object that's passed in. If the class differs from this object's class, then return false. Otherwise, then you can cast the object as a set and then compare them. Go through them field by field. So that's usually how we do an equals method.
So if we like to pass it on, then should we do like the out the class equals method, then we have like the else statement.
Yeah.
And then the else statement, and you cast them as an object.
Yeah, so basically, yeah, if these are not the same type, then they're obviously not equal to each other. If they are the same type, then you can cast the object as a set. Because now you've proven that it's a set. Once you know that it's a set, then you can go through the set field by field and say, is the value of this field equal to the value of that field? And you know this parameter O as that field because it's a set. You've proven that it's a set. So this just returns whether or not the parameter object is one is a set and two contains exactly the same elements as this set. However, we're underlyingly representing the values of this set. We're going to go through and verify that they are the same. Of course, order and multiplicity don't matter. So the equals is going to need to be able to handle that. If we pass in a set that has a different order, then it can still be equal to. So the logic for that goes inside of the equals. This is why it's really important because the built-in equals of the whatever underlying structure we're going to use isn't going to work here. If we use something like an array list for this, then the array list equals would return false because order matters in an array list. So we can't just offload this to some other structure's equals. We actually have to implement the logic ourselves to determine how are we going to determine whether these two sets are the same. We want to be able to take the set difference between two sets. So it doesn't make sense now to pass in an object that's not a set. We can't do a set difference between a set and a giraffe. So this will return a new object. It's going to create a new set object, and it's going to add every element that is the set difference between this object and the parameter object. Definitely got those out of alphabetical order. I apologize. I was trying to go in alphabetical order and then I added difference to the last one. Next is intersect. We want to be able to take the set intersect between two sets. So the intersection between this set and the parameter set that is passed in. Just as before, we're going to be making a new set and we're going to instantiate that set with all elements that are shared in common between this object and the parameter object. As the definition of set intersect. We have is empty. We can check the size of the set and we just return true if it's 0, just like we have for every other object that we've made. We want to be able to remove an item from that Boolean. It's going to return true if it successfully removed it, and false if it was not contained in the set. Neither of them should break the object, so we don't need to throw any exceptions for this, but it's important that we determine and we communicate to the user whether the query that they wanted to remove was in the set or not. Just like with add, and we had an add all, with remove, we're gonna have a remove all. It takes a generic collection type, and we'll figure out what the collection type is, go through that collection, and remove all elements from the set that are contained within that collection. It returns true if at least one element was removed, and false if no elements were removed. Which is a little bit counterintuitive. You might think that I wanted to remove everything and you return true if everything from that collection was removed. But no, if anything is removed, we return true. The exact opposite of that is retain all. So we're going to remove all elements other than everything that's in the parameter collection. And again, we return true if at least one element is removed, false otherwise. You have a size to determine the cardinality of the set. You have a conversion method to convert the set to an array, because sometimes that's really useful. We have a union. Those together return a new set containing those elements. So this is the functionality that we want from a set. Thankfully, we're going to put the set on the back burner for a while. I wanted to introduce this idea because the entire motivation of a hash table is we want to be able to implement a set. And we don't want to use this slow list object that has some issues with it, like indexing, like there's issues associated with it. We don't want to use just a list for this. So if we're going to do this, which operations are slow? Add is linear, because we have to search the whole array. Figure out, is it contained in this array already? And since it's not necessarily stored in order, that's going to be difficult. But then, once we identify where it needs to be inserted, since this needs to maintain its sort, then we end up with an O of n insertion because we have to move everything after it out of the way to make place for it in the new sorted list. So regardless of what we do, even if we make the searching process log of n via binary search, we're going to end up with a linear time insertion process. So regardless of whether we have it sorted or not, add is linear. Does that make sense? Questions? Anything I can repeat?
I think I know a lot of stuff.
Yeah. If I ever move too fast for people taking notes, let me know. I tend to do that.
Does union just combine the two sets
Yeah, every element that is in one set or the other set.
and it returns a new set?
Yeah.
Is it gonna have to screen it super the
Yeah. Yeah, if it's in both, we only want one copy of it in the result set. Luckily, we're not implementing one of these anytime soon. I mostly want to talk about what exists in the set abstract data type. So if you see all of this, you're probably thinking, oh gosh, this is what's coming next. And I don't actually know if I'm planning to have people implement this. I want people to implement a hash table. And I would like people to use a hash table for a set, but I think that might be too much. But this set abstract data type is super useful to know that it exists. There is one of these built into Java. So you can use the built-in set. And it's very useful to know for things that actually want to use a set. I actually, in compilers last quarter, one of their programming projects, people were very curious to learn that they didn't need to implement their own set. And they didn't have to use a list and do all of the associated logic with a list to implement the idea of a set. They could just instantiate a set and all of this was handled underneath the hood. Okay, you can't instantiate a set. There are two main implementations of the set interface. There's the hash set and the tree set. We'll talk about the hash set eventually, before we talk about trees. But yeah, there are two different ways to implement a set. One with a hash table, one with a tree object. But they're super useful for things. They save you a lot of time. Are we gonna move on? All right, so we determined that add is slow. Remove is slow because we need to figure out where the query is in the array, and exactly the same issue. If it's sorted, then we need to compress the list. So even if we have a log n searching time, we would then have a linear time removal process. So no matter what we do, we end up with either linear search or binary search plus a linear time removal process. So again, linear and linear for each of these. And the same logic that we have for add and remove extends to most of these other operations. And we would rather have something that is faster than this, because something that is faster exists. And as computer scientists, whenever we can make something faster, we want to make something faster. Any ideas of what we could do? How could we implement a set in a way that makes add or remove not linear?
I know the answer to that. You use like a hash function so that like the key of it hashes to like the memory location.
Yes. Yeah, we need some kind of mathematical function that's going to turn anything that we could care about, an object, a primitive, something, into a location. So we're going to convert an object into a location. And that way, in an underlying list, we can, instead of searching the entire list, say, if it exists, it's right there. So, two solutions to this, the hash and the tree, are things that we have not seen before. But let's first take it aside and talk about hash codes. Have people seen the hash code function in Java? Have you written a hash code before? A few people? This is something that you include in every object that you write. The reason is that if you don't include it, then it cannot be hashed. So, talking about hashing to an index in an array, we need some way to convert a method into, convert an object into an integer. And this could be any object. It could be a primitive variable, it could be an object, a custom object. We need some way to convert that into an integer. If you use a built-in Java object, every object that comes in the library has a hash code method that does this. Anything that you create, on the other hand, does not have this, and you will need to include it if you would like your end user to be able to use it in a hash table. It's expected that it can be there, so you can override the hash code method so that you can store your objects in a hash table. There are two big goals of a hash code method. One of them must be adhered to, and the other one you're going to do your best to adhere to. So each object must have one and only one possible hash code. That means if the dot equals between one object and another object returns true, their hash code must return the same integer. So I have two different person objects, each of which are an exact clone of me. They should have the exact same hash code. So this is the one that must be true. Two equivalent objects have the same hash code. If they don't, this entire process breaks. The one that we would like to adhere to, if at all possible, is that a particular hash code should map to a unique object. Now, this cannot always be true, but if it can be true, you want it to be true. You may find that you have two completely different objects that by chance happen to generate the same hash code. But since you have control over this entire function of how this hash code is made, if it's possible, there may be a separate hash code function, a different hash code function that you could write where this second one would be true. So in a bit, we're going to talk about the hash code design for different kinds of objects to show how you can maximize the chance the second bullet point is actually true. So not always possible. Where it's not, we want to minimize the overlap. If we determine that it's not possible, we don't just want to give up and do anything. We want to make sure that, okay, there's going to be overlap. Let's mathematically minimize that overlap. Questions on hash codes so far? We're going to see a lot more detail about them for specific objects, but I'm hoping the idea is starting to become clear what we need to do with a hash code then.
How do these apply to deep and shallow copies?
So a shallow copy just says that it's the same memory address, which means there's only one object. So if you were to call two different references hash code that pointed to the same object, you'd be calling the same function. There's no way that can be. For deep copies, you have two different objects that are exactly the same. Now you're running two different hash code methods. And this first bullet point needs to be true, where you want the output from the first hash code method to be exactly the same as the second hash code method from the two different objects. So you can't have any randomness in the hash code method. You can't like generate a random integer, for instance, because then two different copies would generate two different random numbers. We can't have that. So we need some mathematical way for two different objects that are exactly the same to produce the same hash code, always. Great question. Other questions? So the process we're going to go through in general, we're going to talk about this in more specifics here in a moment. But for every field of the object, we're going to recursively call that field's hash code. And we're going to construct some kind of expression. We'll talk in more detail about what that expression looks like that maps into a final integer representation. So we're breaking down the object into its components and using its components hash codes recursively to construct this object's hash code. So this is the introduction to hash codes. We're going to come back to it after we talk about the hash table. Questions so far? Yeah,
So like in Python is a dictionary, just doing that kind of under the hood.
yeah, so a dictionary is what we know in Java as a map. And a map has a set for the keys. They're basically keys mapped to values. The keys are underlying a set.
Okay.
And the values are underlying a list of values that map to that particular object. So a dictionary is basically a hash under the hood.
What's an example of minimizing overlap?
That's a great question. We're actually gonna talk about that a little bit mathematically, but you have to start to think about things like, okay, how many objects do I have? How many possible values do I have? How many, when I go through that hash, how many places are there for each object? So basically trying to figure out, okay, there are 4 billion possible integers. I'm only using 1 billion of those 4 billion possible integers with my particular function. That's not good, and it creates unnecessary overlap at times. So if you can find a mathematical function that can actually spread out to all of the integers and create a uniform distribution where each object is equally likely to be any one of the 4 billion possible integers, then you have something that is good. But you may find that you have a function that even if it's possible to make all 4 billion integers, more likely creates something in the 1 to 10 range because of some bias or some underlying mathematical reason. Then what you don't have is a uniform distribution, you have something that looks very not uniform. And that spike from 0 to 10 is going to create lots of lethal collisions. That means that these are going to map to the same places. Since multiple objects have the same hash code, those hash codes are going to hash to the same location to say it should be stored here, except now that we're going to have lots of objects that are all pointing to that location, which tells us that we all want to store it in the same location, which is going to be an issue.
So for like a big set, then it's not necessarily possible to eliminate them. You
Yeah.
should accept.
Yeah, we're gonna talk about collisions and what we can do about collisions, but the mathematical thing we can do before we even worry about collisions is avoid them where possible. So the hash code's job is to avoid running into collisions wherever possible. And then we'll have a separate set of algorithmic techniques for handling collisions when they occur. We'll talk about those hopefully today. So a hash table, the goal is of course to get faster adds and removes. If we know where in the array to go look without searching, then we can say, if it exists, it's going to be at that location. If we're trying to add, it says, go right there and add it there. We just hope that place is empty and there's not something already stored there. It's less likely that something is already stored there if we've minimized the collision logic in the prior slide. If our hash code is generated well, we'll maximize the chance that when we go to add something in the array, that space is empty. And we can just put it there. When we go to remove, we can just point and say, if it exists in the table, it's going to be right there. We don't have to search the entire array, it's going to be right there. All of this is optimistic, assuming there will be no collisions, because if there are collisions, we have to handle that collision somehow, which means that we might have to do some searching, but hopefully not the entire array's worth of searching. So to do this, we're going to end up using the power of modular arithmetic, because the hash code is going to generate a really large integer. And we're not going to instantiate an array of 4 billion elements. That would be ideal. We would love to be able to do this. We would have a perfect mapping between an object's hash code and a location in our table. We're going to make the table as large as we reasonably can get away with, or is fine for an initial set. But we need to worry about how many things are we trying to store in this table. So if you take this hash code, mod the table size, you get an index stored in. And that should create a uniform distribution across all of the table elements, regardless of the size of the table. So we're going to take the elements hash code and we're going to mod it by the underlying array size. So let's say we determined we have enough space for 5,000 elements. we take our hash code that is some integer between negative 2 point something billion and positive 2 point something billion, and we mod it by 5,000. And that would give us an index into our array where we want to store that element. Or find that element, if it's already stored there. Does that make sense? So if we have access to an object's hash code method, we can always generate the hash code, mod it by the table size, and that will tell us right where to go look for it. So I've already explained some of the issues with this, that we can have two different hash codes that mod the table size, end up having the same location, that point to the same location. So the issue is that multiple objects are going to map to the same index. As our array size gets smaller and smaller, this issue is going to get worse and worse. As we try to store more and more items in our table, this is going to get worse and worse. So, as always, I love to do this. Let's analyze the extremes. An array of size 1 would have every element mapped to the same index. No matter what your hash code is, you mod it by 1, you get 0. Since an array of size 1 only exists at index 0, every element would map to the same index. If we had some kind of infinitely large array, wouldn't that be nice? Then each element could map to a unique index if and only if our hash code method had no overlap. Each object that we could possibly generated a different hash code. Then an infinitely large array would have the space to store each element, and there's no way we could possibly have multiple different objects want to be stored at the same place. So here's the ideal case. Here's the worst case. The reality is going to be somewhere in between. Questions on the concept of a hash table? It is just an underlying array. It's a list again, but the way that we're figuring out where to store and where to look for things has nothing to do with the underlying array's index. It has more so to do with this hash function that we are generating and applying to all of the objects that we want to store in this array. As always in this class, we have some kind of trade-off. And we find that that trade-off is almost always between space and time. The amount of memory that we want to dedicate and the amount of time that we have. The more memory we can dedicate to a problem, the faster we're going to be able to locate things. The less memory we have, the more collisions we're going to have, the more searching we're going to need to do to figure out where this object is. So if there's no space limitation, then you want to make an array that's the same size as all of the possible values that we might want to hash. That's a very optimistic scenario. It's not actually feasible in practice. If we have no time limitation, we're not going to die. Our children aren't going to die, and the sun isn't eventually going to swallow the earth. Then we would just use linear search for every major operation. And this becomes too slow for practical use in large projects. If you're doing some toy project, of course, linear time adds and removes aren't actually that big of a deal. But if you have a database of something that is a real-time access database, like a live server, then you want that to be fast. If you're doing something like having some kind of real-time communication on an online game where you click, your character moves, the monster's attacking, you need some real-time communication between that. You don't want these lookups to be slow. Slow means lag. Lag means players hate you. So in real life, we're going to use caching because we have both space and time limitations. So we need to accept the fact that we can't be perfect, but we can be as good as we possibly can be. So what we actually do involves analyzing the problem, analyzing how much space we have, and knowing mathematically when it makes sense to do things like change the table size. All right, so let's talk about how we actually compute the hash function. The goal of it is to, of course, scramble the keys to create a uniform distribution. We talked about this a little bit. Each index into the table has the same number of keys that map to it. Since there are going to be more possible keys than we have array indices, we want to make a uniform distribution that says that there are an equal number of objects that map to the same destination. As an example, let's take, we want to hash some phone numbers. We have space in the table for 1,000 phone numbers. What would a reasonable hash function be to create a good uniform distribution? I give you a bunch of phone numbers, and they're going to be as spread out as possible. Try to create a simple hash function for this. What a simple hash function that would hopefully create a uniform distribution look like? We need to map a phone number into a number between 000 and 999. The first one that you might think of is something like, well, let's just take the first 3 digits of the phone number. Is that a good idea? Why is that a bad idea? They might all be in the same area code. Everybody from Spokane, for instance, would map directly into index 509. It's like a great idea. How many collisions are we going to have if we're storing 1,000 Eastern students? That's going to be a big problem. Literally everything is going to collide. What would a better hash function be?
Here goes one of the second part.
Maybe.
Maybe like use some function to like take the phone number and then put that into like a 0 to 1 and then multiply that by like a random range between 0 and 1,000.
There are definitely good ways, there are very good ways to do this mathematically. I would argue there's a good, simple way to do it.
Didn't we use the thing where we just mod like all of them, but I mean now the.
We could take this as a large integer, and then we could mod it by the table size. You would get exactly the same distribution as if you just took the last 3 digits of the phone number. Those are pretty equally distributed between 000 and 999. So this will be a much better hash function. We could get tricky if we wanted to. We could produce something that is also uniformly distributed. But why make something more complicated than it needs to be? So in general, the challenge is that we need some kind of different approach, some different hashing approach for every possible key type. So we attempt to offload this work into the hash code method so that the end user does not have to think about it. That means that as part of designing an object, we need to figure out some solid way of hashing that object to adhere to those previous 2 constraints. So let's start talking about, in practice, what does hash code design look like? So for primitives, if we have an integer, just return the value of the integer. That's its own hash code. It's already an integer between -2 billion and 2 billion, so just return that integer. We're usually not hashing just integers. For Booleans, we're gonna return some prime if it's true and some other prime if it's false. For reasons that we will see momentarily. Doubles is a little bit harder. Because the underlying representation of doubles is not the same as you might expect. Does anyone know how doubles are stored underneath the hood? So let's say we want to store some number like 3624439.73264. What's another digit I don't have? 0, 5. Is this possible? Can I store this in a double? A double is a 64-bit, it's twice the size of an integer. Representation that's going to kind of split this down into the number raised to a power, because you could represent this as kind of 3.6244397326411105 times 10 to the what? 1, 2, 3, 4, 5, 6. So every underlying double has a representation like this. So the important values here are the number and the power. You can represent any double by this underlying representation and this underlying representation. So we break this double down into two components, an integer representation of this number and an integer representation of this power. And then from this, we can calculate whatever we need to, making the assumption that these bits represent this value. So this is kind of the IEEE 64-bit representation. So if it's not already stored as an IEEE 64-bit representation, then you convert it to an IEEE 64-bit representation. And then you are going to XOR the most significant 32 bits with the least significant 32 bits. Does everyone know what an XOR is? That's an exclusive OR. If we're going to draw a truth table for an XOR, we're going to have the value of the, let's call this the most significant, the least significant, and then the associated XOR. So the most significant bit can either be a 1, 1, 1, 0, 0, 1, 0, 0. And the XOR is going to be 1, an exclusive OR says that it's one or the other, but not both. So true, true, false, false. It's an inclusive OR would say that both is true, an exclusive OR says one or the other, but not both. So we end up with this associated representation. So you're going to take the most significant 32 bits, because remember we had that 64-bit representation, you're going to throw the most significant 32 bits, 1, 0, 0, 1, 1, doesn't matter what this is, and you have the least significant bits. And you're going to come up with an XOR. That's why I use my pens. You're going to come up with an XOR between these two numbers, where you're going to take this and this as this and this, and then you're going to do a lookup into this table and come up with 1 XOR 0 is 1. 0 XOR 0 is 0. 0 XOR 1 is 1. And then you're going to convert this into an integer. Since an integer is 32 bits, this XOR is going to be 32 bits, it represents an integer, that's your hash code. Does that make sense? The way you do this in code is actually much nicer. In Java, you just have, this is the XOR symbol here, the caret. If you ever tried to use the caret as exponentiation, and then just be like, what is this result? We're actually taking a bitwise XOR. And then this is just saying, take the bits and break it into two groups of, just look at the last 32 bits. So the bits XORed with the 32 bits, so it basically splits it in half and does exactly this. So this is just a bit shift. Advanced stuff that you can just do. You can do this in a lot more lines of code than this, so this is just a very quick, easy way to do this logic. That's all that's doing. Wanted to draw it out so that it wasn't just, what the heck is that? So we're taking an XOR of the most significant 32 bits and the least significant 32 bits. We're way out of time. We'll come back to this and look at how to find hash codes for more stuff. Eventually, I guess we'll decide tomorrow morning. I guess I said that we would do some study stuff. So we'll do some study stuff tomorrow. That's probably fine. I don't know if you get the time he'll take it.